Yeah.
I feel like I've seen it before somewhere.
Now, the fairly simple for the most part.
Yep.
Right? Getting to draw. I mean, being able to draw a left rectangle, right, trapezoid, midpoint, that kind of thing. Now, the thing about the trapezoids, let's talk about that a little bit. I don't remember which one it was. Was it number 4? Again, the rule for a trapezoid, let me do one that would be a simple one. The second trapezoid in would be here, because they're too wide, so you take this point, and then it'd be this point, and you connect them, right? And then you draw there, and you draw it down like that, and you have a nice trapezoid, okay? Well, the first one, well, that's weird because it's below and then it's above the x-axis, but you do exactly the same thing. You just say, okay, here's my left edge. I'm going to take that point on the curve. Here's my right edge. I'm going to take that point on the curve. I'm going to connect them, and then I'm just going to draw to the axis there and draw to the axis there. Now, it doesn't make a trapezoid. It makes what? Two triangles. But that's okay. It doesn't matter. And the formula, when you expand it, you don't have to worry about it that way either. You don't have to say, oh, geez, I got to do 2 triangles. No. Write out your trapezoid. So that first trapezoid would be 1/2 f of -5 plus f of -3, and then times the width of 2. And you don't even have to, because we're going to do problems where we write out the trapezoid approximation without ever looking at a graph and without ever drawing them. And the nice thing to know about that, a problem like this shows us that we don't have to worry about it. We don't have to worry about where those points are, because look what would happen. What's f of -5? -2. What's f of -3? +2. And so we get 0 times 1/2 times 2 is 0. We still get the area that this would create, which is 0. So we don't even have to worry about it. So the way you draw the trapezoids is the same way you draw any of them. You go to the left edge, go up to the curve, go to the right edge, go up to the curve, and connect them. Even if one's negative and one's positive, you still do the same thing. And then you draw it to the axis, and you have the area, because the area is always between the curve and the axis. Okay? So, and then like the third one isn't a trapezoid either. It's a triangle. Right? It's right there. But that's okay. The formula will still hold for the correct area. All right? So with that said, that's about all there is to it. So what we want to do today is go and take and extend this idea of these approximations to get ourselves, to talk about the actual area under the curve. I mean, yes, we can do this to get an approximation. Now the problem is, if I don't know, if we have a problem where we can't do the antiderivative and we want to do an approximation, 4 rectangles doesn't do a very good job. 4 trapezoids isn't bad, but what if we want 3 decimal place accuracy? What are we going to need? More. We're going to need like 20 or 50 or 100. And we certainly don't want to do that by hand to add up all those. So what would be a way that can we come up with a way that could compact that a little bit so we could add 50 rectangles easily and quickly? And we're going to do that, and that's what we're going to work on today. So it is quite exciting, I think. I don't know, but we'll see what you think when we get there. So look in your book here. There's a let me see. I think I've got it up here somewhere. Yeah, right here. Couple of just comments about then just this is one of the pages of the book. It's got some left rectangles, got some right rectangles, got some midpoint rectangles, got some trapezoids. Okay, so the basic idea of approximating the area under the curve using those geometric shapes. All right, and then this picture here kind of shows the idea that we talked about. Okay, 4 left rectangles don't do a very good job of approximating it, but 20 would do much better. And probably 50 would do even better, and so forth, so on. Okay, and then I want to make one other comment about this Riemann sum thing that we wrote yesterday, that big definition. That definition had a couple of key parts to it that were kind of complicated, But it was when we had the C sub I. Let C sub I be any sampling point in the subinterval. Well, what that meant was we don't have to pick the left edge or the right edge or the midpoint of the interval to go up to the curve to get our height. It could be anywhere. You look at this one. Here's a rectangle where the height looks like it's a little left of center. Same with that one. This in this rectangle we use the right edge. And same with this one. And then this point looks like it's a little right of the middle. Fine. This is still a Riemann sum. Remember, Riemann sum means what? R for Riemann, R for rectangle. A Riemann sum is simply an adding up of rectangles. That's all it is. This is a Riemann sum. What else do you notice about this one? They're not the same width, and that's where we put in that delta x sub I, meaning the width could be different. Okay? And so these are a little wider and these are a little narrower. Whatever. That still is okay. It's still a Riemann sum. A Riemann sum is just an adding up of rectangle areas. All right? However many. This is 6. We could have 100, whatever. Okay, so just a little bit of that notation. And so, wow. Did you hurry?
Well, I just showed up, and apparently it was toward the end of class. I played the song once and then came back.
Then came back. Okay.
Don't you love it?
All right. Did you do your homework?
Yes, I did.
Ah.
Well, you get out. Look, it is right in this.
Right.
Uh-huh.
Okay, we just talked about the homework just a little bit, and then I don't know if you had a question, but we were talking about the trapezoid one.
Yeah.
Like that first one, you just take that point, connect them. It's not really a trapezoid, but it's two triangles, and we talked about how the formula still holds, you know. The same. Okay, so onward today then. So what we're going to try to do is try to come up with some notation and a way of writing these rectangles so that we can handle 100 rectangles or 1,000 rectangles or whatever, however many rectangles we want to handle, okay, without getting overwhelmed with calculations, all right? And so there's several things we'll bring in, and then we will try to let that then lead us into a way of seeing something where our notation and all this comes from that we use for integrals. And so it's kind of neat when we get it all wrapped together. So first thing I want to do is this. I want to write down, so I have everybody write down here just a general way of writing, essentially like we did on the homework, these four sums we're talking about. Left, right, midpoint, trapezoid. Okay? And it's, you don't have to draw this, but let me just draw this up here from yesterday. You don't need to do it again, but remember we said A, the beginning of our interval, B is the end of our interval. We said we're going to label this x sub 0 and label this one x sub 1, x sub 2. The last one was going to be x sub n. And what would be the one right before it? Yeah, x sub n minus 1. So we'd have, so we're just starting at x sub 0, that's the left edge, there'd be the right edge, so our interval goes from A to B, and then our subintervals are, okay, labeled that way. Okay, so that's the notation we want to use. So our first left rectangle would be here. Oops. I should look at it. Okay, that's bad. Okay. So our first left rectangle would touch the curve right there at x sub 0. So when we go to write it, okay, here's what you might want to write down then. Our first height we would write as f of x sub 0, and then times, that's our height, and then times our delta x. And then plus f of x1 times delta x, and then plus dot, 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 and then all the way, and what would our last one be? Wouldn't it be n minus 1? Yes, it would be x sub n minus 1, because our last left rectangle would not touch the curve at the far right edge. It would be one width short. Let me go back to that. So if our last left rectangle would actually be, right now, that's my curve not very good because it's almost touched both of them. But our last left rectangle would touch the curve at x sub n minus 1. All right, r sub n would be very similar, but just differ in what way? Starts at x sub 1 as our sampling point that we plug into the function, and then f of x sub 2, and I just want you to be familiar with this notation so when you see it, it's not, you know, overwhelming or puzzling to you. It's really well stuff. When you look at that, I would want you to see rectangle areas. I would want you to see height times width, height times width, height times width, height times width. Height times width is area. Area of a rectangle. And then we're adding up the rectangles, okay? So that's what you see when you look at that. Now, midpoint is a little more interesting to do. If I come back over here and I talk about a midpoint rectangle, what's the midpoint between here and here? I guess we could say, well, we could say half a width, but I'm thinking about what I put inside of my f here. I could do f of x sub 1/2. We typically don't do that, no. How do you calculate a midpoint here? Yeah, now we're not going to. This would be the more formal way of writing it, would be that. You average the x sub 0 and the x sub 1. I mean, if you really were having trouble figuring out what the middle was, but usually it's not hard. I mean, if this endpoint is 2 and this one's 5, we go, well, it's 3 and 3.5, right? Between 2 and 5, halfway is 3.5. We just calculate it kind of in our head. But that's what it is, right there. I would prefer to just, because I think that just makes it, you know, yeah, needlessly complicated, I think. So I'm just going to do it this way. We're going to call it M1, midpoint 1. So the first rectangle height is evaluated at the first midpoint. We'll just call that M1, and you'll calculate it on your own as you do the problem. And then this is M2 times delta x, and then dot, dot, dot. And then this would be the nth midpoint. You had n rectangles, okay? So of those three, the one we work with the most, because we're going to be talking about patterns and looking for patterns and so forth, the one that if we have a choice, notationally, not calculation-wise, calculating them, they're all about the same. I mean, just you got to figure out the point, you plug it into the function, you times by the width, you know, whatever. But notationally, which is what we're working on today, we would prefer to pick the right one because it starts at 1, it ends at n, instead of starting at 0 and ending at n minus 1, and then the midpoint one, you have to kind of figure out what the midpoint is, so that makes it tougher. So you have to do that average thing, so we usually avoid that. So notationally, the right one is the nice one to work with. And it doesn't really matter if you're going to do thousands of them, they all will give you a good estimation. All right, last one is trapezoid. Trapezoid is just always a little longer to write. So trapezoid, so what would be my two bases for my first trapezoid? F of x0, f of x sub 1. Okay, and then times the delta x. So there's the first trapezoid, and then the second trapezoid would use x1 again, and then x2, right? Because remember, x1 is the right edge of the first trapezoid, and it's the left edge of the second trapezoid, and then dot, dot, dot. And then the last one would be what? Yeah, x sub n minus 1 plus f of x sub n times x. All right, now later on we'll talk about some ways we could reword this, especially when we get into ones where we don't really care about how it's written and what the pattern looks like and so forth. We just want to calculate them. Like, for example, on these first three, we can just factor out a delta x, right? Like you can just take out a delta x if they're equal widths. You can just take out a delta x and then have f of x of 0 plus f of x of 1. The reason I don't like to do that too early, though, in these problems is I want you to see rectangles, right? I want you to see height times width, height times width, height times width. And if the function doesn't have equal widths, then you can't do that. You can't factor out a delta x because they won't all be the same. So I really want you to think of this in terms of adding up rectangles, and then this, of course, is adding up trapezoids. Because we will do a thing with trapezoids where we factor out a 1/2, we factor out a delta x, and we look in there and we say, well, look, there's 1x sub 0, but there's 2x sub 1s, 2x sub 2s, on and on and on. So we will get into that a little later, but for right now, we'll just leave it at this. All right, so then, next thing. So we see these, what we have here is we have this pattern. We have these things being added, and they're in kind of a pattern. Well, I want to remind you here of something that you learned, I think, a year ago, and that is
It's been a while.
sigma notation. Was that last year? I think. And you should have, in advanced math, done some stuff with sequences, series, and so forth with this thing right here called sigma notation. Okay? Now, sigma is a Greek letter S, so therefore standing for sum. And we've got several things going on here. The I is called the index. Now, just like we use X and Y for graphing, and we use A and B for the endpoints of our intervals, and we use U and V when we're doing U substitution and integration by parts, we use I, we use J, we use K, typically when we do this notation. And those of you that were in computer programming know that this was like our loops that we did, our 4 next loops. Remember that? For I equals 1 to whatever, for J equals 1. Same kind of thing. It's very, very similar idea. It's an incrementing variable. And what we have at the bottom of the sigma is we have our beginning value. It doesn't have to be 1. It can be 1. It often is 1. But it can be something else. And then we have our ending value up here. Okay? And it always has to go by 1s. You know, in programming in those loops, we could go by different amounts if we wanted to. But in sigma notation, it always goes by 1s. All right? And then in here, we have some sort of formula that when I is a 1, and then when I is a 2, and then when I is a 3, and then when I is a 4, it generates the different terms of the sequence. And then we add them up, because that's what sigma means. Sigma stands for sum. So we add them up. So if I take an example problem, okay, so that's my basic sigma notation. So if I take an example here, like, well, this is always an interesting one, this first one. This always seems like we start with a confusing one here, but what the heck. So this is saying to add up 3 as I goes from 1 to 8. Well, when I is a 1, what do you get here? What about when I is a 2? 3. When I is a 3? 3. In other words, there's no I in the formula, so it doesn't matter what I is. So how many 3s are you going to have? You're going to have 8 of them. Right? You're going to have 8 of them. So the answer is 24. So now, and the sequence we go through here a little bit is kind of what you're going to be doing in your homework today a little bit. The homework starts with some simple things like this. Just some sigmas, just expand them out, simple expansions. In that case, that's a really simple one. Okay? But that I is a 1, you get 3. I is a 2, you get 3, so forth. Now you go over to number 2 here. Right? Now when I is a 1, you get 1. And then when I is a 2, 2. And then 3, and then 4, and then 5, and then 6. But you can see what we're going to do with this. What we said we wanted to do is take these rectangle sums. If we have 100 rectangles, we'd like to write it in a more compact form so we don't have to write out 100 rectangles. Well, that's what sigma notation does. It takes a sum of, in this case, 6 things and allows us to write it in one compact form. Now we go ahead and add this up. Anybody done it yet? 21. And that's the answer to that problem. And then there's another one here. This is, you don't have to write this one down, but so now this one uses J. So J starts at 1, and you square it, and then 2 squared, and then 3 squared, and so forth all the way up to 7 squared. Right? And so we would add this up. I think we did it in the other class. I think it came out to be 140. I think, when we add up the perfect squares from 1 to 49. Okay, so you get something like that. Now there are a couple of formulas for sigmas that we can deal with. They're going to look pretty similar. If you have a sigma of a sum, like an A plus B kind of thing, you can split it apart into two separate sigmas. If you have a constant inside of a sigma like this, guess what? What happens?
This sounds familiar.
Okay? Now, so part of your homework, so on your homework you'll have some problems like this. So for example, let's do number 6 here. Work out number 6 real quick. Let's work out number 6. Humor me. I know, it's easy. It's easy. Now, by the way, speaking of calculator, our calculator does have sigma notation on it. If you want to get your calculators out, because we are actually going to use that here in a little bit, your calculator does have sigma notation on it. So you can type that in just like that. Okay, the sigma, it's in the same place where your integrals are, and your limits and derivatives in that same menu. Says what?
Just kidding. And let it run. Yeah, but I equals 2
Oh, okay.
That says 65.
Now, does it let you put an I in there, or does it have the I in there? So you can put in whatever variable you want. Yeah. So you can use I, J, K, X. You know, it doesn't matter. It's just traditionally I, J, K. Those are the ones that are typically used in sigma notation. Now, how about doing that in reverse? We're not going to spend a lot of time on this, but I think it's one of the things you did last year. It's called nth term formulas. In this case, it'd be.
I was bad at that.
In this case, it would be ith term if we're using I. But could you generate that sequence? Now, when I used to teach trig, the way I used to talk about something like this is look for the pattern that's going on here. Now, the pattern, if I gave you those 5 numbers, what's the first thing that comes to mind for the pattern? Plus 5, plus 5, plus 5, plus 5, right? That's a very common pattern. But you notice in the formula, is there a plus 5? What is there? Well, yeah, there's a minus 2, but I was thinking of the 5. It's times 5. Well, why, if you're adding 5, would the formula have a times 5? Well, think about it. What is multiplication? Repeated addition. That's what it is. When you learn multiplication, 3 times 8 is 3 added up 8 times. I mean, that's what it is. And so multiplication is repeated addition. So when I got a problem like this and I saw repeated addition by 5, that told me that this problem was going to have a 5i in it, for sure. Then all you have to do is let I start at a 1 and see if it gives you what you want. So when I start this at a 1, I get a 5. And then when i's a 2, I get a 10. And then when i's a 3, I get a 15. And what do you notice about those numbers? They're all too big. So all I'll do is take away 2, and I'll get it. See, and that's how you can think your way through them, okay? Now, we're not going to spend a lot of time, hardly any time, doing that. What I do want to tell you is that if I would have written these numbers a different way, I'll bet you could have got it. If I would have written 3 as 5 times 1 take away 2, and then written 8 as 5 times 2 take away 2, and then written 13 as 5 times 3 take away 2, and then written 18 as 5 times 4 take away 2, and then written 23 as 5 times 5 take away 2, could you have found a pattern? I think you could. I'm confident in you. And what would you notice? You'd say, well, gee, the 5 is in every one. The minus 2 is in every one. The only thing that changes is this goes from a 1 to a 2 to a 3 to a 4 to a 5. That'd be a great place for what? That'd be a great place for the I. And so you get 5. So the point I want to make to you is when you have a bunch of things added up, the way, if they're written in a nice way, the pattern can be very easy to see. And the formula that generates it can be very easy to obtain. And that's going to happen in the problems that we do. Okay? So that's just a little side comment I wanted to make about that. Okay. Next step is what happens. That's all well and good. But what happens if we get this problem right here, number 14? Why don't you like that?
What's the 2's a lot of it? Lame.
Because there's how many of them? 30. And what we want to do is we want to not do 4 rectangles like you did on today's homework or 5 rectangles. We want to do 100 rectangles or 1,000 rectangles. And we're not going to want to have to add up every one of those. So the problem we just did a minute ago, we wrote out all 5, we added them up. Now, yeah, we have the calculator. We can just type it in singular text. We're not going to do that. But there is a shortcut. Okay, there are some shortcuts. Now, let's go back to, let's go back first to this, and there's a little bit of a story that goes with this. And supposedly the story, it's not a great story. Don't get your hopes up, but the story goes there was a famous mathematician named Gauss, and supposedly when he was very young, maybe kindergarten, whatever, he was probably so smart, he was out misbehaving, he was bored, whatever. And the teacher sent him to the back of the room because she was tired of dealing with him and told him to add up the numbers from 1 to 100, thinking that this would keep him busy for quite some time. Because he's like a kindergarten or whatever. And so sends him back there, and like 15 seconds later, he comes back with the answer. How did he do? Anybody ever seen this?
Is it like you take, oh yeah, you take the first and the last and
Oh yeah, I remember.
You pair them up. So if you take the first and the last, you get 101. If you take the 2 and the 99, you get 101. If you take the 3 and the 98, you get 101. And how many pairs like that would there be? There'd be 50. So 101 times 50, you multiply that out, and it's 5,050, and that's the sum. So the story goes. Whether that really happened, I'm doubtful. But that leads to a nice formula because honestly, this is just a sigma I equals 1 to 100 of I, right? That's just that sigma right there. And the way you can do, and that would work for any of these, whether this was 100 or not, because the 100 comes from, the 100 is 1 more than the number of terms, so that'd be 101, times the 50 comes from what? The number of terms divided by 2. So in general, if this was an n up here instead of 100, this would be n plus 1 times n over 2. And actually, we could just put the bar across like that. And that would give us the sum of that sequence. And there are some others like that that can be helpful. So, yeah, the most helpful, just type in your sigma notation like that. We're going to do it all for you. But this can be helpful, and we're going to use it in a way that's going to kind of make sense for things that we have. So if I go back to this little sheet here, I've got 4 formulas that I'd like you to write down You're not going to have to memorize them. On our next quiz, I will have these formulas up at the top of the page for you to use. Okay? The first one is sigma of a constant. Now we saw that example with the 3. If you do a constant and add it up n times, that's just going to be c times n. Whatever the constant is times how many times you do it. So that's easy. The next one's the one we just did. If you have a sigma I from 1 to n, you get that right there. Okay? And so these formulas are called the summation formulas, and there'll be a section in your homework where you'll do some of these. Okay, the next one is I squared, and we saw that pattern a minute ago with the 140, right? We had 1 plus 4 plus 9 plus 16, right? We went up to 7. So that's how you would use these formulas. If this was a 7 right here, while you're writing it, I'll just do it here. So if this was a 7 up here, I equals 1 to 7, we would just put a 7 in here, a 7 in here, and a 7 in here. So that would be 7 times 8 times 15 all over 6. Let's see, 6, 2 goes into there, 2 goes into there, 3 goes into there, 3 goes into there. 5 times 4 is 20, 20 times 7, voila, 140. So it's a nice shortcut way, and of course that's a really nice way if I had 100 of them. If I had 100 of those, I'd put 100 in for n, and I would calculate it out. Okay, so it's a nice way of doing the summations, and then there's one for I cubed as well. Okay? So if we need these, you will have access to them and will not have to memorize. So, on our homework here, there will be, for example, let's look at a problem like 16 here. All right? So what do you suppose we could do to get a problem like this using those summation formulas? Break it apart, and the 4 on this one could come outside. So I would rewrite this as sigma 1 to 60 of I squared minus 4 sigma I plus sigma, like so. I could split this apart, do individual sigmas. Now, you may have seen one of the problems I did do there. If I had like I minus 2 quantity squared, I'd want to FOIL that out. I squared minus 4i plus 4, that kind of thing. I'd want to FOIL it out first so it looked like this. Then I could split it apart. Okay? Also, notice that the summation formulas all started at 1. You need I to start at 1 for those to work. Now, before we go, well, let's finish this, and then I want to talk about that. All right, so on this one, what was the formula? It was n. Was it n? So that'd be 60 times n plus 1 is 61 times 2n plus 1. So 121 all over 6. This one would be 4 times, and then this was 60 times 61, right? N times n plus 1 all over 2. And then plus, and then this one would just be 2 times 60, right? 2n, 2 times 60. And then we would add all that up, add, subtract, whatever. And anybody got that yet? Yeah, it's not a big deal. Really, I mean, I think we can do multiplication, division, subtraction, right? 66,000 or something seemed like it came out. Seems like it should be more. That number sounds familiar because we were laughing about somebody mentioned it. 36666. I think it's something like that. Okay? And so I may, just so we can use those formulas, I may ask you, on the quiz to use a formula. So I want to see your work. I want to see your setup. I want to see you split it apart, do that thing. You'll get to use a calculator to do obviously the calculation at the end. All right, so just a little bit on that. Now, the comment I wanted to make, the comment I wanted to make was I said that in the summation formulas they had to start, the I has to start at 1. So if I had this, you could not use the summation formulas. However, you can always rewrite any sigma so that it starts at 1. Instead of going from 3 to 6, it would go 3, 4, 5, 6. So it would have to go 1 to 4. Now, look, so think about this. This would be 9 plus 16 plus 25 plus, now, not that we're going to have to do this much, if at all, but it's important to know that you can do it, okay? It's kind of like a horizontal shift is what it really is, okay? Because now, this first one is 3 squared. So how could I write this? So my first one would be 3 squared. If I starts as a 1, right? On this one, it's 3 squared, then 4 squared, then 5 squared, then 6 squared. How about if I just put I plus 2 in it, right? Isn't this one just kind of a shift left? Instead of starting at 3, I start at 1. Isn't that like a shift left of 2? So couldn't I just take that and essentially change it? And those two are exactly alike, right? Those two will give you the same answer. They'll give you 3 squared plus 4 squared plus 5 squared plus 6 squared. But this one we can use the formulas on. Now we'd have to FOIL that out first and split it apart. Okay, but the formulas only work if I starts at 1. But any sigma can be rewritten to start with whatever number you want it to. All right? So that's kind of an important little idea to understand. All right. Last thing I think on the sigmas before we get in. Actually, that's probably all I need you to be able to do with the sigmas. Okay, so now we're ready to roll. So, yeah, we're not rolling. This was all just introductory stuff. Now we're ready to go. This was like the warm-up. Yeah, this was the warm-up. Now we're getting into it. The race is about to start right now.
I don't like running.
I'm serious. Okay, so here we go.
No, man.
Yeah, that was just
That was perfect.
That was just a warm-up. That was just a warm-up. Okay? So, yeah, turn the page. New page. We better start with a new page here now.
Yeah.
Okay.
Let's get going.
We'll take a little stretch break partway through because it'll be intense. All right, but here's where we're starting with right here. Okay, here's what we're going to start with. Now we want to tie all this together. Now we want to tie the rectangle sums. Obviously, are an approximation of an integral, and we can write sums now. We understand with this sigma notation to kind of shorten our sum notation. So that'll be good. And then see how this ties into an integral. Now, this is one we can easily do and just get the answer. And so I know it's kind of, why do we got to do all these other things? Well, you'll see. So a couple things about it. First of all, we understand that this is the area under a parabola, x squared. It's like this. Pi would be over here somewhere. So we're talking about this piece of area right here. We could do our fundamental theorem on this, which would be 1/3 x cubed from 0 to pi. So that would equal 1/3 pi cubed minus 0, which would just be pi cubed over 3, correct? So we know that's the exact area. Can somebody give me a decimal of that, just so we've got it? For comparison here. 10.335. Okay, so this piece of area in question, we know to be that. So we'll come back to that later on. But what I want to do right now is a little bit like we did yesterday. Let's write out let's write out an R4 approximation. I'll give you a few minutes to write that out. Let's use the F notation. This will be our f of x right here. Our f of x is our x squared. If you want to define f of x in your calculator to be x squared, if you want to type in define f of x equals x squared, that could be okay. You wouldn't have to. I'm going to show you how we'll type it in without the f notation. But for now, we want to write it out like you did today in f notation. Go. And you can help each other out, visit with each other, that's fine. Now keep working, but the first thing you did was what? Delta x, right? The width. How wide are the intervals? That might have been the very first thing, but you get very far into it, and all of a sudden you go, oh wait, I got to figure out how wide these are. And so the delta x on this one is pi fourths, right? Pi fourths. Okay? So each subinterval. And I would like you to go ahead and calculate it out as well. And probably give it as a decimal, yes. So I'm going to put up here what I've got so far. I haven't calculated it, but see if yours agrees. Okay, and so it's a fair amount to type. This will be the last time today you have to type, 4 of these things in, like this. I like that way of thinking, Miranda. Miranda said on the bright side, we don't have to do it all in our head. That's right. Be thankful for what you've got, right? God, I got to do all the 4 of them. What? Let's do it by pencil and paper, and we can add some things, right? I like that. Good. All right, anybody getting something?
Yeah. It's taken.
That sounds reasonable. I think it is 14 something. Sure. 15 something? think it's, well, maybe I,
I got something.
oh my.
I got
14.5, okay, so seems to be at least a majority getting that. Now,
I don't know.
but let's listen, let's shorten it a little more. If only we had some way of writing a sum in a more short and compact way.
Oh, if only.
If only.
Oh, what was us?
Thank you, Mr. Sigma. Right? Now, Brittany says, gee, Mr. Clark, you're dumb. 4 pi fourths, well, she didn't say quite like that, but 4 pi fourths is just pi. And 2 pi fourths is just pi half, right? Why didn't you simplify those? Why didn't I? Because now, when it's in the sigma, this is going to be a lot easier to write. So not simplifying them is actually easier because my I is going to go from what to what? No. Okay. Think about this. I is going to go from 1 to 4. Remember, the I is from 1 to n. It's how many things you're adding. The I is how many things you're adding. So we're going to go from 1 to 4, and we'd like to start the sigma at 1 if we can. This is why we did rights and not lefts. To be honest with you, it makes them easier. Remember I said the rights go from 1 to n? It's going to go from 1 to 4. Now, when you write your sigma, think about that one we did a minute ago. Where was that? Oh, it was on another page. Right there. No, I guess it's gone. But all you do, listen, all you do is you say, okay, every one of these terms, look, every one of these terms has an F in it. Doesn't matter what I is. Every term has a parenthesis like this. Every term has a 4 in the bottom. Every term has a pi fourths out at the end. You notice that? What's the only thing that changes? 1 pi, 2 pi, 3 pi, 4 pi. So what goes in here? I pi. That's right. And you might have run to write that way because if you flip them around, pi I is kind of hard to say. I pi, whatever. But you see what I mean? Well, I guess I could have said, yeah, the pi is in every one. The only thing that changes is number in front of the pi. And it goes 1, then 2, then 3, then 4, which is a perfect place for the I. So if you write them out in a nice way so the pattern's easy to see, then the sigma is very easy to write. Now, usually when we do the sigma, though, we want to take one more step and take it out of the F notation. Now, in your calculator, if you'd already put the defined f of x to be x squared, you could just type it in like this. But I want us to get in the habit of taking it out of the F notation. Now, how do we do that? Well, f of 2 means put a 2 in for x. F of a means put an a in for x. F of I pi over 4 means put an I pi over 4 in for x. So we're going to take I pi over 4 and square it times pi fourths, right? And that's going to give us, now I'm going to let you go ahead and type in your calculator, but then I'm going to show you something else we could do with it. Go ahead and type that sigma into your calculator. And hit probably Control Enter so you can get a decimal. You get the same thing? And that would have been a little faster than having to type in 4 of them. Okay, 4 of those rectangles. So the sigma just allows us to do that. Oh, it's not plus pi fourths, it's times pi fourths.
No, I got the right answer before too. I'll figure it out.
Yeah.
I'm a smart girl. At least that one.
Oh,
Yeah.
on the square, yes,
It's-
good.
You have to type another parentheses.
Yeah, well, actually, yeah, we had trouble with this one too. When you get I pi over 4, and then there's these parentheses, you don't get your cursor outside the parentheses, get your cursor outside the fraction,
Yeah.
and then hit square. And then it'll throw in parentheses and square. So get the cursor off the top and off the bottom and off to the side of the fraction, then hit square, and it'll do it. Okay? All right, now, let me show you what we could have done, what we did in the old days. Okay? Before this fanciness. It is this right here. Let's look at our sigma. And now let's come back to those sigma formulas, those summation formulas we were doing a minute ago. I could take this and I could simplify this with some algebra. I could make this you don't need to do this right now. We're going to do it here in a little bit. I could have done this, right? And then I could have put that together as I squared pi cubed over 64. Now, pi is a constant, so pi cubed is a constant. 64 is a constant. What can I do with that constant? Bring it out in the front. So I could take pi cubed over 64, and I could bring it out in front, which leaves me just a plain old sigma I squared, which I can then use my formula. My formula for I squared was n, which is 4, times n plus 1, which is 5, times 2n plus 1, which would be 9, all over 6, right? So what is that? Let's see, 6, 3 goes into there twice, 3 goes into there. No evens tell me that. 6 times 5 is 30. Wait a minute.
Fine if we don't.
Wait a minute. 30 pi cubed over 64, is that what we had?
Yeah.
30 pi cubed over 64. Okay, we go out by the weight room.
Can we get our jackets out in our locker?
Yeah, I suppose, real quick. Hey guys, out by the weight room, across the thing there. Somebody must have pulled this because this was not a planned one.
Again.
Can I go barefoot? This was.
God, this
Oh. Can I share with you?